Our story begins approximately 4.6 billion years ago, in a time when the universe was still young and full of potential. Imagine a vast cloud of gas and dust, a nebula adrift in the cosmos. This nebula was a chaotic, swirling mass of particles, each one a tiny fragment of the universe's grand design. This swirling mass, the remnants of a long-gone star, held within it the building blocks of our solar system. It was a cosmic nursery where the seeds of planets, moons, and even life itself was sown. It's a humbling thought, isn't it? To think that everything we know, everything we are, originated from such a humble beginning. We, in all our complexity, owe our existence to this diffuse cloud of cosmic debris. Each atom in our bodies was forged in the heart of a star, scattered across the universe, and eventually brought together in this nebula. The nebula, like countless others scattered across the universe, was neither calm nor static. It was a dynamic, ever-changing environment full of energy and potential. It churned and roiled, stirred by shock waves from distant supernova and the gravitational pull of its own mass. These forces acted like a cosmic blender, mixing and churning the gas and dust within the nebula. This constant motion caused the particles within the cloud to collide. These collisions were not random. They were the result of the complex interplay of forces within the nebula. Some collisions were glancing blows, others head-on crashes. Each collision was a tiny step in the process of creation, a moment of transformation. Each impact, however, transferred momentum, sending particles spiraling inwards. This inward spiral was the beginning of a grand dance, a cosmic ballet that would eventually lead to the formation of our solar system. As more and more material drifted towards the center, the nebula's core began to collapse under its own gravity. This collapse was a critical moment, a turning point in the story of our solar system. This collapse triggered a chain reaction. As the core contracted, it heated up, converting gravitational energy into thermal energy. Temperatures soared as gravitational energy converted into heat. The core became a furnace, a crucible where the elements of the universe were forged. The core, denser and hotter, became a beacon in the darkness. It was a sign that something extraordinary was happening. A new star was being born. It was the nascent sun, our very own star, starting to ignite and burn. This was the beginning of a new chapter in the story of the universe, a chapter that would eventually lead to the formation of the planets, including our own Earth. Over millions of years, the remaining gas and dust in the nebula would coalesce to form the planets, moons, and other bodies of our solar system. Each one a unique world with its own story to tell. Among these new worlds was Earth, a molten, turbulent planet that would eventually cool and develop the conditions necessary for life. From the chaos of the nebula, a new home for life was born. As the Earth cooled, water began to accumulate, forming oceans. In these primordial seas, the first simple life forms began to emerge, setting the stage for the incredible diversity of life we see today. From single-celled organisms to complex multicellular life, the story of life on Earth is a testament to the power of creation and the incredible journey that began in a distant nebula 4.6 billion years ago. With the sun ablaze at the center, a colossal furnace of nuclear fusion, the remaining gas and dust continued to swirl around it, caught in a gravitational dance. This swirling disk, called the solar nebula, was far from uniform. It was a turbulent, ever-changing environment. It was a chaotic mix of elements forged in the hearts of long-dead stars, hydrogen and helium, the lightest elements, which were the primary constituents of the early universe, along with heavier elements like carbon, oxygen, iron, and silicon. These elements were created in the fiery deaths of previous generations of stars, through processes like supernovae and stellar winds. These elements, the building blocks of planets and life itself, were scattered throughout the disk, waiting to be assembled into new worlds. Within the solar nebula, a delicate dance of forces was taking place. Gravity, the force that binds the universe together, was at work. Gravity pulled everything towards the center, drawing particles and gas inward, creating a dense core, but the sun's heat also pushed outwards, creating zones of varying temperature and pressure. This outward force counteracted gravity, creating a dynamic equilibrium. This interplay between gravity and heat would ultimately determine the fate of the material within the disk. It was a cosmic balancing act, with each force playing a crucial role. Close to the sun, where temperatures were scorching, only the most resilient materials could survive. These materials included metals and silicates, which could withstand the intense heat. Here, rocky and metallic grains began to clump together, forming the seeds of the inner rocky planets, Mercury, Venus, Earth, and Mars. These protoplanets would eventually grow into the terrestrial planets we know today, Venus, Earth, and Mars. These planets formed in the hotter inner regions of the solar system where only rocky materials could condense. Further out, beyond a region known as the frost line, temperatures were cold enough for volatile compounds like water ice, methane, and ammonia to freeze. This region marked a boundary where different materials could condense. Here, in the realm of giants, the seeds of Jupiter, Saturn, Uranus, and Neptune began to coalesce. These gas giants formed in the colder outer regions of the solar system, where ices and gases could accumulate, and Neptune began to coalesce. These planets would grow to become the massive gas giants that dominate the outer solar system, each with its own unique characteristics and moons. The story of our planet's formation is one of gradual accumulation, a process known as accretion. It began with microscopic dust grains, remnants from the original nebula, colliding and sticking together within the swirling disk. These initial clumps, held together by electrostatic forces, were minuscule, barely larger than a grain of sand. However, over millions of years, these tiny particles continued to collide and merge. As they grew larger, their gravitational pull increased, attracting even more material. These larger aggregates, ranging in size from meters to kilometers across, are known as planetesimals. The early solar system was a crowded and chaotic place. Planetesimals, numbering in the trillions, whizzed around the sun in a celestial shooting gallery. Collisions were frequent and often catastrophic. Some planetesimals were shattered into fragments, their constituent materials scattered back into the disk. Others merged, growing ever larger and more massive. Section 4. The Giant Impact Hypothesis of Violent Birth. The early Earth, a protoplanet still in its infancy, was a hot and volatile world. It was a time when the solar system was still young and the planets were in the process of forming. The Earth, just a newborn in cosmic terms, was a seething cauldron of molten rock and metal. Its surface was a chaotic landscape, constantly reshaped by the forces of gravity and the relentless impacts of space debris. Its surface, bombarded by a relentless barrage of planetesimals, was a molten sea of magma. These planetesimals, remnants from the solar system's formation, rained down on the young Earth, adding to its mass and heat. Each impact was a cataclysmic event, releasing immense energy and causing widespread melting and vaporization of the surface materials. The constant bombardment kept the surface in a state of perpetual turmoil. Volcanoes spewed forth lava and gases, while the nascent atmosphere, thin and toxic, offered little protection from the harsh radiation of the young sun. The volcanic activity was intense, with eruptions occurring frequently and violently. The gases released from these eruptions, including water vapor, carbon dioxide and sulfur compounds, contributed to the formation of the early atmosphere. However, this atmosphere was far from hospitable, filled with toxic gases and lacking the oxygen necessary for life as we know it. It was during this turbulent period, approximately 4.5 billion years ago, that a cataclysmic event occurred. The solar system was a dynamic and violent place, with planetary bodies frequently colliding and merging. It was in this chaotic environment that the Earth experienced one of the most significant events in its history. A Mars-sized object, which astronomers have dubbed Theia, collided with the proto-Earth in a colossal impact. Theia, a rogue protoplanet, had been wandering through the inner solar system, and its path eventually intersected with that of the young Earth. The collision was not a glancing blow, but a direct hit, with Theia striking the Earth at a high velocity. The energy released in this event was unimaginable, dwarfing the power of all the nuclear weapons on Earth combined. The impact generated temperatures and pressures so extreme that both Theia and a significant portion of the Earth's mantle were vaporized. The energy released was equivalent to billions of megatons of TNT, far surpassing any explosion humanity has ever witnessed. The impact was so violent that it ripped a chunk out of the Earth's mantle, flinging molten rock and debris into space. This material, a mixture of vaporized rock and metal, formed a vast cloud around the Earth. Over time, the debris began to coalesce, drawn together by the force of gravity. This debris, caught in the gravitational pull of the Earth, coalesced over time to form our Moon. The process of the Moon's formation was relatively rapid in geological terms, taking only a few million years. The newly formed Moon was much closer to the Earth than it is today. and its gravitational influence played a crucial role in stabilizing the Earth's axial tilt. The impact also tilted the Earth's axis, giving us our seasons, and sped up its rotation, shortening our days. The axial tilt, or obliquity, is responsible for the seasonal variations we experience, as different parts of the Earth receive varying amounts of sunlight throughout the year. The increased rotation rate meant that days were much shorter in the early history of the Earth, gradually lengthening over billions of years due to tidal interactions with the Moon. Section 5. Cooling down, a planet takes shape. The impact that formed the Moon was a defining moment in Earth's history. It also marked the end of the planet's initial accretion phase. The solar system, once a chaotic shooting gallery, was gradually becoming a more orderly place. Most of the planetesimals had either been swept up by the growing planets or flung out into the depths of space. With the bombardment subsiding, the Earth began to cool. The molten surface solidified, forming the first crust. Water vapor, released from the planet's interior by volcanic activity, condensed in the atmosphere and rained down, forming the first oceans. The early Earth, however, was a far cry from the blue planet we know today. The atmosphere was still toxic, devoid of free oxygen. The continents, as we know them, had yet to form, and life, that most extraordinary phenomenon, was still billions of years away.